Hey everybody, Dave Limerick in Hong Kong with a new episode of the THD Podcast. Today we have the technical advisor from the UltraWide Band Alliance joining us. This is kind of something I've been personally interested in finding out more about how this technology works in the RF audio space. We're gonna try to dig in on that and learn as much as we can. But without delay, let's give a shout out to the Alti Association, our sponsor, and we encourage everybody to get out and join Alti and find out more about that great industry association. So, without delay, today we have a special guest host, Colin Ward from CareTech in the
Hey,
Philippines. Good morning, Colin.
morning, Dave.
All right, and Jackie
Okay.
Green, the technical advisor from the Ultra Wideband Alliance. Thanks for joining us, Jackie.
Sure. Hi, everybody.
All right. So, yeah, we've been directed to Jackie from several people that are working with ultra wideband as kind of a point of great information related to this RF protocol. What is it exactly? So, this is my
Oh boy.
curiosity. So let's maybe get into something and explain to people how this technology works and how it relates to audio.
Okay, I'll try. It's a big
Okay.
topic. All right. So, yeah, my path to UWB has been pretty interesting because it came through audio, not through location or real-time location or sensing or anything. I was vice president of engineering and R&D for Audio Technica for a lot of years, and we made a lot of wireless of all sorts of using all sorts of technologies, anything you can think of. But as people know, probably the spectrum that's being used for wireless microphones has been shrinking and shrinking. We lost 700 megahertz. We then lost to 600 megahertz. Now they're talking about taking more.
Mm,
When this started happening, I started looking for technology that would be able to deliver the full audio quality and the full bandwidth and the reliability that we would need, but not be subject to the spectrum crunch problems. I tried a lot of different things. I flew to Israel and talked to a PhD RF guy over there, um, listened to what he said was the best spread spectrum digital audio, and was kind of underimpressed. Basically, my comment
mm.
to him was, "Well, it's noisy," and he said, "It's digital; it can't be noisy." And I said, "All right, so thanks very much. Goodbye." But I'd been reading a lot of papers because you're looking for something to work, and the UWB topic kept coming up. And when you do the math, 500 megahertz of bandwidth and the data rates, and the bit depth that we wanted to do for pro audio, um, there was plenty of room there. I mean, the math worked. So we said, well, let's look at this UWB stuff. And that was before the FCC actually even approved it. But we started researching it, and it really was doing what we thought it could do.
Mhm.
Really, truly delivered full audio response and dynamic range with very little latency, and was pretty stable. So the first, the first FCC approved professional wireless microphone product hit the market in 2007. It's a long time ago. That was our SpectraPulse conference system. We did a conference system on purpose because nobody knew a lot about UWB back then. And so we wanted to use it in a controlled space. Conference rooms are
Yeah.
inside. They're kind of similar sizes, and you kind of know in advance the number of people that might be in them. So we learned a lot working in the conference systems. I used that system as a microphone system for presenters at a tech conference in 2009, and one of the people attending the tech conference was a high end and a engineering manager from one of the broadcasters. And he said, "Hey, we've got this spectrum problem. You know about this?" I said, "Yeah,
Mhm.
that's why we did UWB." So they encouraged us to look at pushing the boundaries and getting it working more for a live broadcast and live performance setting. It took a few years, but as a result of that, we did have a successful product. And we created a company called Alteros, which existed only from 2016 to 2019. But during that time, we designed and produced right here in Ohio and delivered quite a few professional broadcast and live sound wireless microphone systems that worked great, still work great. Over time, Audio-Technica decided to resorb that company. That they brought them back in-house because they were interested in broadcast as well. And we went on to form a company called Nexonic. And Nexonic was able to, now it wasn't working for one company. So now I'm able to work on wireless for any company and improve lots of different audio and wireless products and work on lots of different UWB projects, including consumer projects. So the UWB front kind of expanded. While I was doing all this, I had been working alongside the UWB Alliance as a member and joined them as a technical advisor. Trying to think when I probably did that, around 2020 probably. And the UWB Alliance is an interesting organization because it's full of the people who are really trying to make UWB work. But we're also able to raise the visibility of what it does and help it to be successful and successful with the global regulators as well. So the last piece for the slide on here, which is all part of my UWB story, is that in my past, I was a vice chair for standards committee for microphone specifications at the Audio Engineering Society and participated in the digital mic interface standard in the writing of the digital mic standard. So I knew that that was going to be the right vehicle for getting a standard written for UWB audio. It's because it matched really well with the digital mic interface work. And yeah, well, we really wanted UWB to be, for this application, to be driven by the audio and not by the location and sensing and all the other cool things that it does. So that's my path for how I got to UWB.
Okay.
But we probably should talk about what UWB is, huh?
No, for sure. But it's also cool coming, especially in the audio industry, people that come from the pro space are always, I don't know, nicer, but also like they're more into audio rather than just shipping volume of stuff, So
Yeah.
it's and also just the quality that you need. I know the spec in pro is so tough to meet. So that's a very, very cool place to start to try to achieve what people would want in pro or consumer.
It is, because UWB is a pulse that happens in time. And pro people are used to talking about jitter. And they're used to talking about parts per million. They're used to talking about keeping things tight. And if I talk to like just a normal digital radio person about that, their eyes kind of glaze over and they're like, why are you worried about that? So I really enjoy working the UWB in the audio space. So, and it's amazing. Hopefully this information I give you today will help you understand why I think it's so amazing. So first of all, UWB is just a pulse. It's basically the radio that Marconi developed. It just bursts a bunch of energy into the air. That's it. It's 500 megahertz wide. By definition, it's 500 megahertz wide, or it has a 10 dB bandwidth that's greater than 20% of the center frequency. On the screen there's a picture of a pulse of screen capture from one of my scopes of one of the pro audio systems that I did. It's a funny shaped little burst of lots of information. You take the analog to digital converter. It's just like normal wireless. Up in the front, you take an A to D converter, which honestly, that's where most of the latency comes from. And you put it into a digital signal. You organize your frames and packets, kind of depending on, are you doing Manchester encoding? Are you doing syncing? Just all the different things you need to know. And you pick a desired modulation form and you send these 500 megahertz wide pulses. And those pulses are sent like digital streaming sequence. So again, that's a real comfortable way for audio people to think about how am I getting my signal. There is not a continuous carrier wave, which is one of the magic pieces about UWB. Also, an important thing to know is that because it is just digital pulses in time, it's super easy if you have a closed system, to run a TDMA system, which lets you have a lot of control into a lot of things. But on the right, you can see those little spikes those 2.5 nanosecond spikes,
Mm-hmm.
that's the signal in time. And you can see that 98% of the time, there's nothing there. So 98% of the time, it's just silence. And that helps UWB in a lot of ways because makes it really secure. You can barely find it. It's only there for 2 nanoseconds and it's gone. It also means that it doesn't interfere with itself, and because there's all sorts of free time, and it doesn't interfere with other services. So that short duty cycle is one of the pieces that helps UWB be kind of magical. The other piece is the fact that it doesn't have a continuous carrier. And so normal wireless that everyone's used to talking about, like Wi-Fi or Bluetooth or even the really good digital wireless systems that I really respect,
Mm-hmm.
um, they are subject to multipath interference and signal fading and additive and subtractive properties that can distort the signal. Whereas if you just have a pulse, it's just a pulse, and so it doesn't get distorted. I'll go to the next slide. I think I've got the yeah.
Mm-hmm.
As long as the receiver sees the pulse at the right point in time, you have your entire signal. One of the other reasons UWB is so stable and so cool to work with is because it's a really wide bandwidth. It's 500 megahertz compared to a tiny little FM signal, or compared to like spread spectrum, which could be 50 megahertz, or you could add into their Wi-Fi, which could be 20 or 80 or 120, or maybe someday a little bit more.
Mm-hmm.
But so significantly, proportionally, when you're doing the math, the interfering signals aren't a big piece. You've got a lot of signal there that you still have to work with. You've got a good signal noise ratio. Another interesting thing that people don't realize is, and that drawing on the right, UWB is by law everywhere required to sit in the ambient RF noise floor. So most countries, and the US included with the FCC, have a regulation for what they call unintended emissions, unintended spurious emissions. So every electronic device, whether it's a wireless device or not, my computer or lighting walls. Their lighting walls are infamous for sparing electromagnetic energy. All these devices have to be tested by the regulatory bodies, and they're unintentional radiations. So the electromagnetic stuff that comes off because of the clock frequency or whatever has to be below minus 41 dBm per megahertz. So all sorts of stuff already operates at that top, at that noise floor, and UWB has to operate below that. So we're really, really invisible. It's pretty cool.
Okay.
So like I said, as long as the receiver sees that pulse at the right point in time, you have your entire signal. As opposed to, if you look at the top box, that's a UWB pulse. And if you look at the bottom box, that's a typical frequency carrier-based frequency modulated wave. And you can see that it's continuous and it can be stretched and pulled and added to and subtracted to, which can't happen to a UWB pulse. So I love the picture in the top right because when I'm talking to groups of people, or I'm at school or whatever, people do understand what water looks like when you throw a stone in it or when rain hits the top of it.
Mm-hmm.
And that's what happens when conventional wireless is putting their signal out into the air. Those waves, you can have a wave here and a wave here and a wave here, and it's fine. But those waves, if there's too many of them or they're too big, they start banging into each other. And you know what it looks like if a whole bunch are there and it's all chippy choppy. And that's just a completely distorted signal, right? That's what happens with continuous carrier wireless.
Right.
So there's all sorts of things you have to do. One of the biggest things is watching your RF frequency coordination, looking for intermods, so that things aren't interfering with each other. You don't have to do that with UWB because there's no wave there to cause that shape, to cause that problem to happen.
So
it's just those bursts. Yeah, go ahead.
yeah. So how could we make a visual metaphor of, so we have these waves of the water, rain dropping on a
Hmm.
pond, and so
Hmm.
what would be a kind of a visual metaphor for how UWB is
Looks there.
flying through that and avoiding the interference?
Isn't that interesting? So the thing is that the UWB happens at a really specific point in time.
Okay.
So if you're looking at it on a time basis, it's like a teeny tiny grain of sand at a
Mm,
single point in that water,
right.
and because of the power level too, compared to the other services, Wi-Fi or the FM wireless stuff that we use
Hmm.
that can operate up to a watt. Those are big concentric circles, right? It's a
Right.
lot of power. You can look at the difference in power. I'm not kidding. It's like the difference between the top of Mount Everest and a grain of rice.
Right.
So you're in a whole different scale. And so you could put a whole lot of dots of that stuff in that
Right.
space
Yeah.
before you had any problem.
Hmm.
Yeah, it's
So one of
like
the
a
other magic things is device density, right? Because you can get, like, the latest FCC ruling for the latest report and order says that if they're going to do WMAS, which is a really great additional tool for professional microphone users to be able to get better performance out of their traditional digital wireless, the requirement is 18 simultaneous channels. Because beyond that, you start having all sorts of problems. With UWB, first of all, you could do it over and over and over and over and over again. But second of all, even if you're operating in the same space, uh, you can have a lot of devices before that little grain of rice sits on top of another grain of rice.
right.
So the
Almost like
device
a
density is way easier.
almost like probably a bad metaphor, but like a surfboard in a tsunami. It's just kind of it's inconsequential in terms of the wave.
Yeah. Yeah,
Okay.
that's an interesting metaphor. Oh, I might use that. So yeah,
So,
so we don't get the weird physics stuff that happens.
Yeah.
The adding and subtracting and distortion of your sound quality. You don't have to coordinate it. They don't, because they don't intermodulate. And they're this 500 megahertz direct streaming signal, so the sound quality is comparable to any other super high end digital audio gear that's not
Mm,
wireless. I mean, like, if you're running it at 2496, that's what it's going to sound like. Maybe even, I'm going to jump on a limb here, maybe even a little better, because there are also things like capacitive loss over cables or thermal buildup and stuff like that that
yeah.
can actually affect um,
But you're
the
using
physical audio
your
gear.
defining 2496, right? Can you go
Yeah,
higher? Can you go
yeah,
32,
yeah,
190? Okay.
you can.
I
Hmm.
mean, I guess studios would want, the studios want
They're
32-bit, right? And
yeah.
they're gonna want the best they can get, right? The current chips on the market. If you're doing it discrete, you absolutely can do it. And I did my wireless discrete, and so I could do whatever I wanted. The current chipsets on the market are doing 2496 or 192.
okay,
Uh, don't know that I've got anyone with a chipset with a 32 yet, but that's just
amount of
a
time.
matter of time.
Yeah.
Yeah.
What's the
So
can I ask you talked about the
please.
being below the noise floor, right? So what is the
Mhm.
regulatory position on these? What if I'm certifying a UWB product? Is it the same test as normal FCC class 15, or what is it?
The part 15 is the same test.
Right.
We still have to do unintentional radiation. This is really funny though, but because many times the unintentional radiation from the DSP device on the chip or on the device on my board or
It's worse than the radio.
the clock, it's worse than the radio. And so many times what I have to do is I have to send special test software along with the gear that the lab can turn off the UWB and then look at the individual sections of stuff because um, yeah, it's hard for them to find the UWB when the other stuff is it's tricky. The rules, so the unintentional rules are the same. The rules for measuring the actual UWB system, there's that minus 41 dBm limit. There are certain rules that are designed to make sure that you capture it in the right time window, because this is a time-based wireless. Yes. And so there are certain rules to make sure you've captured it in the right time window, because if you don't capture it in the right time window, you may be over or under reporting your true pulse power.
Right.
So there are globally rules for how to measure a UWB signal, and they're not different for audio than anything else. It's all the same.
Yes,
it's all the same. Some countries have duty cycle requirements. Some countries, like Europe, is now opening up, at least for indoor use. They're looking at opening up to the transmit power to minus 31 instead of minus 41. Personally, you don't really need a lot more power, and sometimes more power is worse, because with any RF, if you start putting a lot of energy into a space where there's a lot of things operating, weird things start happening. I'm a major advocate for turn it down and do a better antenna and do a better receiver, because then you can just do more devices. But one of the other reasons I like this slide, one of the other reasons UWB works, and you can see it even though it's at minus 41, is because the picture on the left shows an FM modulated signal, and it's showing how the noise goes along with it. And it can mask the actual signal, and it can be really hard to find. The UWB pulse, though, there's a super steep rising edge. And, because it's really fast, and it's pretty easy once you know where and how to look. It's pretty easy to detect that pulse. So you use slightly different methods, but, good receiver design, good antenna design, and there's a whole lot you can do. So I'm trying to think on my next slide, do I have more? How does it work? No, this slide is about balancing things, though. Mm-hmm. So all digital wireless audio methods have to balance between performance trade-offs. There is no perfect solution or one-size-fits-all solution for any wireless that anybody is doing. Believe me, I looked. And for a while, I tried real hard to make UWB be the solution for everything, because it is so cool to work with. Mm-hmm. But if you have something besides UWB operating, you can balance all these different parameters and choose the right performance focus for whatever your application is, right? So, but when you do that, you start looking at much higher battery consumption, and you start looking at limiting things like simultaneous channels. So if you're looking at UWB and you've got that magic top right corner with that big bandwidth, also, I should have probably highlighted that information rate, because we can send stuff fast with those little pulses. But we kind of automatically, from how audio works, we kind of automatically get a really great frequency response, and we don't need to worry about all the processing and all the other things that happen. So our latency is really pretty much just whatever our A to D was, with a little bit added on for management, and simultaneous channels, like I already pointed out, because of the nature of the device and the pulse space instead of continuous carrier waves. The device density is much higher. But all of these things can be traded off. You can take a professional wireless microphone system right now, and its operating range can be 300, 500 meters or whatever. But then you decide you want like more simultaneous channels. So what you have to do is turn down the transmit power. And once you turn down that transmit power, your operating range goes down. Or maybe you decide you can't sacrifice your simultaneous channels, so you start messing with your frequency response, and you pull your frequency response back from up to 20K to 12K, because a lot of applications people don't notice if you're only going from 20 to 12K. There's lots of things you can. It's always a balancing act.
Okay.
Same thing for UWB. So UWB, the piece that we focus on, that we sacrifice is that operating range more than anything else, because we're operating at such a low power.
Yes.
But I say that with a caveat because there's ways to get around it, but
Right.
it's basically a short range device.
But are you saying that the actual UWB link adds almost zero latency to the system?
It's negligible, really. It's you're talking nanoseconds on a pulse, and something that's hardly ever operating. So when you're looking at proportional things that add up into the latency, the biggest thing is the time, whatever your A to D is doing.
Conversion time to A to D, right?
Well, yeah, exactly. So then you could have a processor. You don't have to have a processor. Like I said, UWB is what Marconi did. I mean, he didn't have a DSP, right?
Yeah.
But you can have a DSP, but it's not hard at all to get the latency below 3 milliseconds. Not hard at all.
That's cool. Yeah, I spent a lot of time in the Wi-Fi multi-room audio space. Latency was
it's
impossible.
tricky.
Yeah, I mean,
Yeah, it's tricky. But UWB now can help that.
Yeah, I can see that.
Because you know what they do? You know what they do? Now we're going to jump in snot in my slides. But they take UWB and it senses the location for the Wi-Fi. It senses the environment for the Wi-Fi. It senses like the distance to the receiver,
Right.
and then it adapts the transmit power so that you use only the transmit power you need and nothing more. And then you start saving batteries and you start getting a better latency number.
Yeah, okay, I can see that.
Very cool.
So
Yeah, very cool.
it is cool. So yeah, UWB's got lots of advantages. From a performance standpoint, because it is just a different wireless, it does things differently. And so it reacts in the environment differently. And so there are specific things that it's better at doing than any of the other wireless methods. I mean, there's a reason the military kept UWB for so many years and they didn't let other people do it, because it's really good. It's really good at some stuff. Ranging and security and precise positioning. Of course, the low latency real-time audio, the high device density, and you don't have to have exclusive spectrum for it either. We operate our 6 gigahertz UWB on right next to 6 gigahertz, the new 6 gigahertz Wi-Fi access points without a problem. In fact, more than once, I've seen the UWB pulses cause a kind of, I don't want to call it tape bias, but a kind of organizing effect, and the Wi-Fi actually the throughput gets higher, it gets better.
Okay.
Kind of a strange thing, but it's really good for some stuff. And so I'm very much an advocate for I use Wi-Fi and I use Bluetooth and I use lots of other kinds of wireless too. But I am really an advocate for using the technology that does the thing the best, because that saves the spectrum the most and that saves the batteries the most. So if you look at the bottom bullet there, eco-friendly, we're using so many batteries. The more mobile devices we get going, the more and more batteries get going. So if you use something that needs, power like Mount Everest as opposed to power like a flea, you can imagine the difference in the battery pileup, right? I do want to talk about coexistence, because a lot of people may have heard about spectrum sharing and coexistence. And the interesting thing about UWB is, because it isn't disruptive, it can operate and does operate underneath as an underlay under all the other types of RF without interfering with it. It's been operating now for close to 20 years. Well, it's been 20 years since it was allowed, and with never a report of interference. And believe me, when I worked with broadcasters developing this, they tested everything, because they can't have interference. I'd have to bring systems and stick it outside the C-band uplink truck. and they'd be watching everything with a fine-tooth comb and making sure nothing could ever interfere because the C-band's at 6 gig as well.
Hmm.
So anyways, coexistence though, it's not the same thing as sharing. And right now there's a really big focus on figuring out spectrum sharing stuff. In fact, this week there's a conference happening over in Europe. And the thing is, sharing is an agreed upon negotiation, right? I agree to give you this and you agree to give me that. Or I agree I'll use this now and you can use this later. Or I agree I can use this in this room and I'll use that in this room. Both parties know about it and it's a transaction. Coexistence, the parties don't have to be aware of each other and it can just happen.
Yes.
They can be aware of each other, but they don't have to. This thing can be running right here and this thing can be running right there, and neither one ever knows of the other one's existence, and no one's performance is compromised. So,
right.
Yeah, I think it's pretty important as we move forward and as regulators are looking at stuff that we distinguish between coexistence and sharing.
Right, and you also have coexistence within the product. I mean, I do products with multiple videos in.
Mm-hmm.
Absolutely. Yeah.
I think
what you're telling me is that I don't need to worry if I've got Wi-Fi and you have UWB in the same product. I don't have a coexistence problem between the two of them.
You do not. That's right. And as a matter of fact, you've got a, let me think, is it on here? It's the third bullet down, support. You've got a support advantage. UWB is already being used in conjunction with other types of wireless to improve their performance.
Right.
And chipsets already include Wi-Fi, Bluetooth, and UWB all on the same chip.
Mm-hmm.
So we talked about the device density and immunity for multipath. That's that you don't have, just like if those waves were hitting a rock wall or a dock or something, they'd be distorted. With UWB, multipath's actually its friend, because if the signal hits a wall and bounces and hits the receiver's still happy, and so you're basically getting more coverage, more possible paths of success when you have multipath. So that's cool. Another thing, and I don't know if people know about this, but because it is a very secure and very limited range under some circumstances, it's in a lot of car locks now to prevent against the man-in-the-middle attacks, where people can sit off to the side and grab your fob RF and duplicate it and open your car and start your car even. Yeah. So it's simple. You can build it with almost nothing. You can build it with a diode. You can just shove a bunch of energy through a diode and that makes a pulse. So you can make things really small. But a cool thing, which we kind of talked about a little bit, and I'll show you a product later that does this. You can fuse communication with positioning and sensing.
Yep.
So, because UWB is awesome at positioning, I think the closest, it's an order of magnitude tighter from a positioning and location standpoint than other wireless technologies. So you can tell I like it, right?
I look at UWB. We do a lot of systems for people tracking, and particularly in medical situations. And UWB is certainly something we look at for that.
Yeah, you can use it for contactless patient tracking, and you can read the monitors and stuff without their pulse, even without having to even touch the patient. It can be in the corner of the room.
Yep.
And you can work room to room to room without the systems interfering with each other. Where if you're using Wi-Fi, that's going from room to room. I mean, I don't know about you guys, but here at my house, I can see and I live on a farm, so it's not like I've got near neighbors, but I can see 4 other people's
I can see a lot of Wi-Fi networks here. Not as bad as Hong Kong. I used to be able to see 50 networks in my wherever I was there. But yeah, it's not as bad. But typically, we don't use Wi-Fi. We use BLE and LoRa, stuff like that. Anyway, sorry, it's go back to
Oh, Laura's cool. Laura's cool. That's getting lots closer to us.
Yeah.
Well, I wanted to include just a couple examples because people don't really understand that UWB already has been used and is truly capable of this high-end audio in really, severe environments. This one example is a theater in New York, and you can see the dates. It was 6 years ago. Frank Filippetti was who's a multiple Grammy Award-winning producer and engineer and mixer, and he was the engineer on the project, and he knew that they were going to have trouble because the theater is low. Besides the fact that it's New York, like Hong Kong, and there's a ton of RF everywhere. It's really hard to coordinate frequencies. But this particular theater is also between two cell phone towers, and traditional wireless just won't work there. So he contacted me and said, "Do you think you could do UWB?" And I said, "Yeah, sure." So we did we had to have low latency and real-time audio. And in particular for this was like a gospel show, and holy cow, I've never heard more amazing singers. And I've been a musician my whole life too. Really super high SPLs. So we had to have that dynamic range. And this was 24 people all standing like right next to each other. And it operated for 5 weeks without a single drop or hit or fade or funny noise or anything. And Frank said that it was the most natural sound I've ever heard in a wireless system, and that he noticed it was never once heard any cracking, popping, or snaps coming from the mics, and that he got the best, most emotional choir vocal sound he's ever experienced. And I mean, that guy's done a lot of stuff. And if he, if he thought it was the best sound he'd ever experienced, that's pretty high praise.
Praise indeed.
And then another example that I included here, and I included this example because UWB is more or less, and one of the reasons I like it is a short range communication method that doesn't pollute the environment with a bunch of unnecessary RF. However, you can use it in big spaces if you know how to do it. So it was used by Florian Brown, working for ESPN in 2018 again at the U.S. Tennis Open. And the U.S. Tennis Open is held at Arthur Ashe, and it's a huge venue. I think it might be one of the biggest in the world. We deployed our system across 3 stadiums and interview areas. And it was at 6.5 gig. And remember, 6 years ago, somebody operating something at 6.5 gigahertz, that was really... That's like the bleeding edge, right? I mean, they were like, "Oh, we're going high," but they had tried it the year before, and they knew it was going to work at those distances in that setting. And like you said, you don't want to have Serena Williams sit down in the chair and not be able to hear her. And it was a big jump, but it was rock solid, and they were really happy with it. So it proved to me it can perform. I mean, 6 years ago, using discrete parts, we were able to do it. So now there's multiple chip manufacturers who've taken up that charge. And they are making high quality, high reliability, real-time audio. And now it's not discrete, so now it's cost effective. So that's why all of a sudden it's turning into an interesting topic. Because once you've got chips, you can get you can get the volume up there.
Speaking of chips.
So, Speaking of chips, later on I've got a list of who I think has chips. But here's 2 examples. So we are moving to practical mass market solutions, which means that these things are showing up at trade shows. And recently at the AES, and there was a really good workshop on UWB at AES this year, and at the Munich High-End Audio Show and Infocom. 2 interesting companies that I've worked with and are familiar with their products are Sonical, and they make a cool remora, they demonstrated UWB operating on their remora device at the Munich High-End Audio Show for 4 days. And this is a trade show with people coming and going and body blocking it and holding it and everything else. And for 4 days with great sound and no problems. And what's neat about their system is that they can use lots of different types of wireless, Bluetooth and UWB and Wi-Fi. and they also connect with their operating system, their Cosmos operating system, which lets you tailor and personalize any headphone or any listening experience. It's with multiple plugins, and it's really cool stuff. So it's not just the great audio; it's this other additional whole system that works really well. Mm-hmm. And then there's Spark, who's a chip manufacturer in Montreal, and also really, I actually have, we've had an FCC approval on a device, and they're also solid, and they know they've learned a lot about audio since they started. I think they originally went towards UWB because they liked the eco-friendly aspects of it, the reducing battery usage and stuff. But as they started working with it, I think they found it actually does really cool stuff, and they've made some pretty neat things out of it. I included this particular slide from them because it's an audio podcast and people want to know about bit rates. So the systems I showed you on the previous slides, our bit rate was between 4 and 6, depending on what we were doing at the time, and applications and stuff. The Spark people here are looking at just under 5 megabits per second. So you take that 500 megahertz wide pulse and 5 megabits per second, and then you just kind of start doing the math, and you're like, oh, we can get a lot of resolution and make things sound really good. Spark's also in this Sonos Faber wireless loudspeaker, which is getting good reviews. And let's see what else. There's close to 1 billion UWB devices already in the market, and there's like many years worth of over 5 years worth of phones and stuff on the market using UWB. So It's really funny because a lot of times people don't even realize. I was at a conference in Washington, D.C. last month, and these are wireless people. And we were talking about this. I was talking about UWB, and he came up to talk to me after the panel. And I said, well, you have an Apple phone? Yeah. And he pulls out his keychain. He's got a tag. I said, you've got UWB? He said, I do. It's interesting because it works so well that it doesn't ever cause anybody any problems, right? So it's kind of cool.
Do you see that? I mean, this was a question I had. Kind of the sources. Okay, it's great. The kind of the source of the audio. Do you see, for example, the phone guys like Apple? Are they going to start sending the audio on UWB?
I can't speak for what Apple's going to do because, man, they're a giant big machine that never likes to tell people what they're doing. I hear rumor. Sorry, you go ahead.
No, go ahead. Yeah, they are a big machine. But what's the rumor?
They have their own chip.
Of course they do.
Yes.
So I don't know fully how their chip works. They developed their own chip quite a while ago, actually. Which that's a fair amount of support for you to be. Other companies here use off-the-shelf chips from the standard manufacturers, and there are rumors of a kind of jailbroke Samsung doing audio. There's no reason not to. I mean, a pulse is a pulse.
Right.
So it's just a matter of the code telling it what to do, and if someone knows how to do that, they can make it do it. Right. So it's not happening now, but I won't be surprised when it does happen.
Yeah. I believe they can do it. And actually, just a side story, I was friends with one of the guys from Decawave, and he was always approaching Apple, and then they turned around and made their own chip to his chagrin.
They made their own.
Yeah. But anyways, all right.
Well, that's Apple for you, man.
Yeah.
They're a big company that spends a lot on R&D.
Yeah.
And they don't like to tell people in advance what they're doing. So here's a cool application. So this Bang & Olufsen speaker They use UWB to track the listener, and then they fine tune the audio delivery so that whoever you are, you're always in the acoustic sweet spot. And I think that's just brilliant. And then there's this headset, which I know for sure uses a Corvo chip.
Yeah.
And it's a gaming headset, and I've listened to it and walked it out from a range standpoint. It's very solid. It's a good thing. And the gamers, they really want that they need that super low latency. So
yeah.
I would expect it to be pretty popular technology for that kind of an application.
Mm-hmm.
And that headset also uses a cool antenna, which you see the little in the upper right there, the AntennaWare logo. That headset uses that AntennaWare logo, and AntennaWare is a super good antenna. Not just UWB specific, although at AES they were talking about their UWB application for their antennas. But the impetus behind that is what we were talking about earlier, and that's this body blocking and sphere of influence kind of problem and keeping the power low. Some people, especially 6 years ago, when we were putting systems on the market, like in a belt pack or handheld, some people would say, "Oh, you can't use UWB because there's body blocking." Well, body blocking isn't a UWB thing. Body blocking is an RF thing, and at certain frequencies, your body, it'll either absorb or reflect them, depending if it's skin or muscle or whatever the tissue is. And once you get higher, it just is an issue. So the picture on the left shows like imagine you're in a subway train, right? And you got a bunch of people sitting there, and you got the picture on the left, and the guy's got his phone in his back pocket, he's sitting on it, and he's trying to listen to his wireless headphones, but it won't work. It won't play the music. So one of the solutions, and it is a solution that's being asked of regulators, let us turn our power up so we can get around body blocking. Well, if you do that, yeah, you'll hear your signal, but you can't control. Well, there is beamforming and everything else, but that's not where we're going with this. You can't really control that. RF goes out into the environment, and now it's interfering. Remember the ripples on the pond. It's interfering with the next guy, or the guy on the back, or the guy in the front, or whatever. As opposed to the picture on the right, where you've got the guy and he's got the problem. He's got his sitting on his phone, but then you've got the guy who's got the AntennaWare antenna. And I'm not joking, this actually works. I've tested that. They're here on my bench. And they use this AntennaWare antenna, and you don't have to turn up the power, and it gets around the body blocking problem, and you can listen to your music. So we accomplished it in my system. Again, it was a discrete system. So we accomplished it with a circularly polarized cross dipole. And there's really cool things that you can do getting antenna. I love antenna stuff because, it's a garbage in, garbage out problem. All wireless can do all sorts of cool stuff, and you can stick a processor on it, and you can filter it, and you can do whatever. But your antenna, it's the first point of departure and the first point of entry. And if it works well, it makes everything else you're doing really, really much better. So if you understand antenna theory, there's a lot you can do to make a really stable system as well. So, and the AntennaWare guys do, and I'm pretty sure they do antennas for other frequencies and other technologies as well. But this particular slide that they had was specifically for their UWB application.
Yeah, I think the AntennaWare guys, they came out of I think well, Johnny came from like Aptex, then CSR, then Qualcomm. So these guys have been doing wireless and are they Irish originally? I think so.
Yeah, they're in Ireland. I think so.
Yeah, because there's AntennaWare and there's another antenna company called Towglass from Ireland. So there must be something in the Guinness over there
that's right.
Helps them with their signal pickup.
Oh yeah, and I love Guinness. Yeah, I love Guinness. That must be why I like antennas.
All right.
That's it. So yeah, no, but so in addition to antennas, you can take this really good tech and you can make it work better. the traditional ways of running with like Bluetooth or Wi-Fi or whatever and doing retransmit and pretty heavy duty error correction methods, they work. They absolutely work. But they don't work, and it's really hard to maintain your latency number nice and low and operate in real time. But on this list of solutions, I've definitely used every one. That you can use digital windowing and MRC and CRC, and you can do forward error correction, especially if you're staggering your stuff and it doesn't contribute to latency. Frequency time, receiver, and phase diversity. Multiple receiver gain stages. That's a really good trick. People should do that more. Multiple transmit configurations and buffered and offset transmit configurations. Pulse positioning and stretching techniques, so you can get lots more data and send it down that pipe and get better resolution. Over-the-air synchronization. This is when the audio, like I mentioned, the audio people understand this because they understand the downside of jitter, and that's basically what you're trying to avoid. It's a digital signal. You need it to be precise. My system ran under 3 parts per million. So, and TDMA, if you have a closed system, you can use TDMA. And adaptive data rates. So if you're not in a totally critical audio situation, where would you be in a totally critical audio situation? A studio. Yeah. But if you're in a studio, there's not going to be a situation where the UWB isn't capable of just operating. But if you're in a situation where, like a stadium or whatever, now the super critical listening, you're not going to hear it if for a second or two you drop out of 2496 into 2448 and then pop back up again. No one will ever hear it, and you won't drop your signal. So there are ways to do that. It happens seamlessly. Obviously, this is one of the reasons why you need audio people doing this, because they need to know how to ramp things up and down, or how to just do stuff so you don't hear an audio artifact. Right. But one of the ways we can really make stuff better is to ensure that devices are interoperable and that they always can work together and deliver the best audio. And so that's why I did this standard group. So it's through AES, it's the SE0202B. And of course, anybody's always welcome to join the standards activities. They don't have to be AES members. The standard will be X260 UWB high-res low latency audio interface. We've already had really outstanding industry response. We've got 52 members, which is a big standards group for the AES, with a lot of big global companies participating. So that means there's a lot of really good ideas flying around. And some of the people are not audio people, and they've come in, and they're joining a standards group in the AES, which I think is pretty cool. It gives us an opportunity to really expand our reach. Our goals are to provide interoperable audio and feature control sets for device compatibility, obviously, because then if everything always works together and we can have plug fests and make sure that everything's cool, that just helps with mass adoption. It helps with innovation. It helps, keep costs down. It's just good for everybody. Assuring consistent audio quality and performance is important, especially when we're talking about an industry that on some sides of it have nothing to do with audio. They're industrial or, robotics people or positioning people or real-time location or whatever. And they don't know what's good audio performance or not, what the specs are behind it or how you accomplish it. So I like it that these people are participating in AES so that we could share that knowledge, and it seems to really be working well. We're going to describe the preferred way to implement connection management. None of these next things, I hope they help point out the fact that we're not going to reinvent the wheel. We're not going to think of some new way to do stuff, because a lot of RF is very well thought out, and there are really good standards, and there's no reason to reinvent the wheel. So we're going to build on and provide extensions to, especially the IEEE 802.15.4AB, which is a UWB standard that's in development. Mm-hmm. So we're kind of developing in parallel, and we'll use an off-the-shelf. We'll use a IEEE standard so that we can use off-the-shelf silicon. Like, yeah, that'll make it way easier if you want to make a phone do this, right? We'll use a standard PHY. There's a number of options of PHY within the IEEE standard, so we'll probably pick 2 or 3 so that people really have a lot of flexibility about how they design things. Same thing with the Mac. We'll pick standard Mac options where it's possible, where it fits with our performance goals. The audio transport, well, this is the Audio Engineering Society, so we'll probably pick an audio standard, AES standard, probably the AES 47, not totally positive. Channel access will probably be built on the ETSI standard, and key management on another one of the 802 standards, 802.15.9. So a few reasons for doing this are to do it with an audio focus, but also to not reinvent the wheel, but also to be able to get it done faster. Because the sooner there's standards in place, the more it will prevent a lot of disparate gear are already out there in the field, because it's already starting to happen. Gear's starting to show up in the field, and right now, it's not necessarily all compatible. Right. So I don't want too much to be out there that's like that. So. Okay. Yeah, I think it'll be good.
Yep.
Oh, look, I'm getting very close to the end. There's a list of who has UWB chips. Yeah. That I know about, anyways. There's probably more. And I've noted on there that Apple has a proprietary chip. Now, I don't think they have just one chip though. I think they have at least 2 different proprietary chips. And I included a global spectrum chart because UWB regulations are different in different parts of the world, but there are places where it lines up in lots of places, like between that 6 and 9 gigahertz region. The United States has the biggest spectrum that's available for UWB. It goes from 3.1 to 10.6. The most popular UWB channels are channels or frequency bands, I guess is what I should say to you guys here, are 5 and 9. So that's the kind of mid 6s, 6240 to 6739. And then the up to the 8s, 7737 up to 8236. And then a lot of the car stuff, I think, happens around channel 6. There is also a fair amount of stuff at the top of 6, bottom of bottom of 7. But there's lots of options there. Some of the industrial control stuff and more commercial uses operates down there in the 3s and 4s. But yeah, it would be really great if this harmonized. I don't know if it ever will. But it's okay, because working from between 6 and 9 that's a lot of spectrum. Right. It's a lot of spectrum, and we can put a lot of devices in the spectrum, so should be okay.
Okay.
So that's my story. That's it.
All right. It's
quite comprehensive. Know what else you might want to know about. A little bit of everything, I guess.
Sure.
Go back to my pulse.
Okay. All right, Colin, do you have any questions?
Well, I've already given a few, but what do you think kind of the maximum range is if you're doing lossless?
So that's a funny story. Our system went like 70 feet. Okay. So the sweet spot, like didn't care with body blocking or anything like up to 40 feet. So clearly like easy in a room. That was with one receiver though. But right. I always ran at least two, but preferably three receiver, because when you can triangulate and get three, you get 20 dB bump with your diversities, and you can then cover a lot of space. The problem though is that that's in a contained space. We originally, a long time ago, when that original broadcast engineer came and talked to me, one of the things they wanted, because they were having trouble, I don't know if you guys know about this, but a long time ago there was a problem with football coaches who talk on wireless headsets, and one of the coaches heard what the other coach was saying across the field or something, and there was all these security problems and everything. So one of the original things they asked for was, and because UWB, oh my gosh, it's not in my slides, UWB is a bidirectional, almost always a bidirectional technology. So they wanted to use it for coach comm and player comms. And I said, that could work, because, we're only going like about 70 feet. So it should be good, because the football field's wider than that. Well, I remember when I said that multipath is its friend, and there's not a wave that degrades. The signal would hit the ground and it would bounce and would come back up again. And so it was going like 300 feet. So we had solid reception with no interference at 300 feet. And I said, okay, this isn't going to be a coach system, because I can't guarantee that signal's not going to head across the field. There are people who do 100 meters, and ranging, for ranging up. I'm assuming you're talking about audio. Ranging applications, you can go really far, because if you change the duty cycle, and the timing, you can go really far. In fact, they used the earthquake that was recently in Turkey, and there were unfortunately a number of people buried in the rubble. They use UWB for that. They can use UWB to find people way down deep through all the obstacles and through a really long distance, to locate. Basically, it can locate a heartbeat, so they can find people, and it can go far. I prefer it not to.
Yeah.
And I always organized my antennas so it didn't. In fact, my receive antenna, transceiver antenna, was shaped more like the polar pattern, and it was more like a shotgun microphone, because I really did want to be in control of where my signal was going or not. I didn't want it to be just on me. But I would say that it's certainly good enough range for any kind of indoor use, and especially with reinforcement from multipath from walls or floors or whatever. And there are definitely situations where it's working hundreds of feet, and there are people who claim that they can do 100 meters with it. So I wouldn't be surprised.
It wouldn't be marketing without claims. So
it wouldn't be, and but it's going to be just like it's going to be just like the other wireless microphone systems, where they say, "Oh yeah, we've got 500 meters." Under some specific condition, absolutely, right?
Yeah.
But then you set up all your antenna distribution systems, and you're this and you're that and everything else, and you don't. However, and what's funny, the pro wireless system market is starting to move this direction too, because they've started to do zoning and multiple antennas and everything else, and it's how we ended up being able to do the Arthur Ashe, the US Tennis Open.
Right.
We can set up zones. We ran it at Disney out in California, and one of the things that they have is this big long parade that goes for forever and ever and ever down the main street, and operating RF there is complicated. It's a complicated RF environment, and it's tricky from a multipath and fading situation. But with UWB, you can create very specific zones, and it can just hand off. So in some ways, it could be unlimited. In other ways, It just depends.
Yeah.
Okay.
Just kind of depends how you've got it set up. It should be, its sweet spot is a short range communication device, though.
Right. Okay. I think that was like possibly one of the most comprehensive and precise presentations on a core technology that we've had on this podcast. So,
Good.
Jackie, we super
really?
appreciate.
Okay.
Oh yeah. I mean, I get it now, but that's great. Hopefully, people watching get it, and we encourage anybody has questions, just pop it down below, and we'll start a little community talking about this and answering and feeding questions around. So, thanks everybody, and please like, subscribe, and share, and all these kind of good things with YouTube, Spotify, etc. And yeah, once again, Jackie, thanks for joining us, and Colin, thanks for taking part in this one. And so, bye bye, everybody. We'll see you on the next one.